let's get cracking, as they say. Right, so we're going to create a new one with the wizard. You can all see that, I hope. Oh wait, I can't click it there. I've got to click it down here. Oh, wait a minute. No, that is the right place. Okay, next to continue. Compounds, we know we need argon. Just conveniently at the front here, we need hydrogen. Well, let's do nitrogen first in the order we've got it here. Nitrogen. Hydrogen. And don't forget ammonia. You see the feed stream, I've given you the components there, but remember that the reactor will produce ammonia, so we've got to add that. And then always delete the search just to check that you've got all of your components there. And next. All right, we're going to use Bing Robinson. And what I forgot to do last time when I tried this Tut is to add next. Have I started the recording? Yes, I've started the recording. Just checking the... Yes, you can. So there's the question, can you add a material if you forgot to put it in initially? And that is by using settings. So that settings up there, you can go back to the questions that are asked in this wizard. Okay, system of units is C5. So that uses pressure as bar and temperature as degrees C. And that's all. Finish. All right, now we're going to put in these things one by one as following each other without any recycles at first, just to check that everything works, that everything is actually working. I'm going to close this thing. Give me more space. The integrator controls, I haven't used them before. I don't know how to use them, but it at least gives me a little bit more space to work. Okay, so let's go to the first one, which is going to be the pressure changer, compressor. Put the compressor on. Click on the compressor. The outlet pressure is what we're going to specify, and that's 200 bar. And we're not going to use adiabatic efficiency. Oh wait, I must hit enter, I think. Right, and then we're not going to use adiabatic, we're going to use polytropic, and 75% is good.
Sorry, Prof, 20 bar.
Oops. Damn it. Okay, I mean, that will be why your thing didn't work. I guess delta P equals 0. So if you make this one 20 bar, delta P equals 0 on all of the components, you will operate the whole loop at 20 bar. And that will change, that's going to change the split at the first compressor. So yes, it should be 200 bar. If you have a look at this flow sheet on the Tut, I made a mistake in changing 20,000 kPa into 20 bar. Annoying. So let's just go along with 200 because that's hopefully going to give us answers that are close to the Aspen simulation that I've shown in the Tut. Okay, so there's the compressor. We've got the 200 bar, 20 bar, and we can put in a feed stream, create a feed stream, and an outlet stream, and an energy stream. I always like to move the energy stream that way. And now we can put in our composition, and that's input data compound amounts. We're not going to use mole fractions, we're going to use molar flows. And we're going to have argon as 0.01. Nitrogen is 1. Hydrogen is 2.5. And ammonia is 0. And not to forget to accept changes. We go look at mole flows again just to see that it's all correct. Yes, that looks right. Okay, so the whole thing is working. We've changed our compressor. We've got a pressure increase of 199 bar. Adiabatic efficiency is 58% because we used a polytropic efficiency of 75%. So this looks correct. Okay, so now we can go on to the next one. What happens after that? We have our reactor. So let's get the reactor out. A conversion reactor. That in there. Now let's add reactions. So this is where we go to settings. This is where you can change all of those things we had in the original wizard under settings. And settings comes out on the other screen. Right, so there's our components. Thermodynamics is Ben Robinson, correct. Reactions. And we're going to add a reaction. We'll use the default set and add a reaction to the default set. It's a conversion reaction, reaction conversion. And oops, I'll pull that up onto your screen. Right, and this is methanol. That's what synthesis? Ammonia synthesis. And we're going to include the argon, the other three. And the base component, the conversion is given as conversion of hydrogen. So that'll be the base component. Stoichiometric coefficient of nitrogen is 1. That's -1. I haven't tried putting in +1 because in Aspen they automatically make that a minus. This thing doesn't know yet, so you have to put in minus, I guess. Not -3 for hydrogen and +2 for ammonia. And there it says stoichiometry is okay. And this is what I got wrong last time. I forgot to change the phase from liquid to gas, and then it said that the thermodynamics don't converge. Caused me a few more gray hairs. Okay, so that looks correct. Now, the stoichiometry and the reaction looks correct. The base component is hydrogen, and the only other thing we need to put in is the conversion, which is 25%, not 0.25, 25%. And that should be okay. So let me try enter. Ooh, 25, enter. Looks good. Then I'll just move settings out of the way. I'm going to close settings. Right, so we've got a reaction for this reactor. The inlet stream is going to be MSTRO2. The outlet streams we must create. And the energy stream we must create. By the way, I know that we're going to have to add a mixer in here because we've got a recycle that's coming in later. So I'm going to move this a little bit away. We can get in the mixer and things. Okay. Whoa. Now, from the reactor to the heat exchanger to the cooler, I don't think there's anything that comes in, so I can put this a little bit closer. Yeah. Now we can put in the cooler. Everything is blue, which is really good. Much better than my first attempt. So we're going to go to a exchanger cooler. In Aspen, you just put in a heater and you can make it a cooler or a heater, whatever you prefer. Click on it and we say we're cooling down to pressure drop is 0, that's fine. Efficiency, heating or cooling, not kilowatts, so we must change this. And we want the outlet temperature to be 40. Enter. No energy stream added yet. Oh, nothing is added. Okay, inlet stream. SDR3. Oh, yeah, not to create. Remove. SDR3. Right, did somebody send a...
No, it's me, Prof. I just want to ask, on the compressor, what do we specify in the calculation type? Because if I specify pressure increase, it gives me an error.
Can I have a look there?
Oh, I see. It's outlet pressure.
Outlet
Sorry,
pressure.
I understood it wrong. Yeah, thank you.
Oh, is that so? That's not the. Yeah, that is the default, isn't it? I don't think I changed this, did I? Okay, fine. Right, so I've just made this thing and I've disconnected it. MSTRO5, and I want to delete it, so I'll just hit the delete button. Okay. So we can, and I have connected the MSTRO3. Let's just choose that. Yes, I've connected MSTRO3, and the outlet is going to be a new one, and hopefully it will make, yes, make it that 5 that we used to have, and the energy stream we must create. Right. And you notice it actually puts the energy stream going outwards when you are pulling out energy. It doesn't need energy. Right, is there no, again, no, now we can go straight to the gas liquid separator. Not compound circuit, this one. We chuck it in there. And we add the inlet stream, MSTRO5. It's got lots of inlet streams, but we only need the one. We've got a vapor stream. We've got a light liquid stream. And we've got an energy stream. That I'll rearrange. All right, now let's have a look at our flow sheet. We want to recycle this one. but I'm not going to do anything with that yet. I want to work on this one, which goes to another. Oh, let me just check the operating inlet minimum. That's fine, but we want to override separation temperature, and that we want to be 40. One click. Focus 40, and override the separation pressure, and that must be 200 bar. Okay, so just for background, 200 bar is a really high pressure for a ammonia synthesis. Typically, an ammonia synthesis will run at about 80 bar, and low pressure ammonia synthesis runs at about 50 bar. But ammonia synthesis is considered a high pressure synthesis reaction. 200 bar is what I found worked very nicely for the separations. So we're cooling down using cooling water to 40 degrees C over here, and that should be 40 degrees C. Yes, it is. And this one is going to operate at I didn't press enter. That thing always catches me. Come on. Why does it not allow both? Right, separation, temperature and pressure. They should be independently available. Right, let's try again. 200, enter. Maybe I didn't press enter after the last 200 bar. And we say last execution run, it's fine. And we have a look over here and we see, and we have a look over here and we see 40 degrees C and 200 bar. Yep. Right, now we can put in the next gas liquid separator. Drag another one in. Okay, I'm going to, let's put it here. And this one has got a feed stream MSDR07. It's got a vapor outlet stream, a light liquid stream, and an energy stream. Right, so what happens to the light liquid stream? That gets recycled. So we're leaving that one for a moment. This one, it seems to be, it's solving, but let's just change the conditions. Now, on the Tut question, I said that the high pressure flash. Let's have a look at the high pressure flash. Sorry, I said 40 degrees C. It is 40 degrees C and 200, and Q equals 0. Oh, it's because the stream that goes into this high pressure flash is at 40 degrees C and 200 bar pressure. Then we go into a gas liquid separator at exactly the same condition. So obviously the energy stream will be 0. It will be an adiabatic. There's no need to add any energy into this unit. This one is different. So when I solved it, I simply used the minus 35 degrees that I knew it comes out at. But let's have a look if we can make the energy stream 0. So outlet pressure calculation is one of the options. Outlet pressure is going. We want to specify it. Right, this is not really specified. We have to override. All right, I don't see an option for making this energy stream 0. So I'm simply going to override the separation temperature and make that -35. And enter. Right. And it ran. Override separation pressure, and that's going to be 1 bar. Enter. And it solves. Fine. Now, in Aspen, we want to put in this recycle that goes the liquid we're recycling to, that's the gas, it's the gas that we're recycling to the compressor. In Aspen, you can simply put in additional inlet streams over here. You can put in lots of inlet streams, same as much like this one, the separators. You can put in lots of inlet streams directly into a separator. The compressor doesn't allow that, so we've got to do a mixer. And I'm going to move that out. I'm going to disconnect that. I'm going to disconnect that stream. And the inlet stream is going to be disconnected. Takes some time, but there it goes. Now we're going to put in a mixer. And this mixer has an inlet stream called MSDR01. And we're going to add this one later. Inlet stream 2 is going to be MSDR08, but we can't add them directly. And I'll explain why just now. So now we've got, well, let me leave it up there. And now we're going to have an outlet stream which we create. And this one is going to have that MSDR10 as its inlet stream. Okay, and we can solve the flow sheet. It should still solve. Yeah. Okay. Now we're gonna. No, it's always good to check that the thing solves, and you could save your simulation to be sure before you start adding recyclers. But now, as I said, you can't just connect MSDR08 directly to the compressor. You've got to mix it first, and then you can add that stream to the compressor. But even that you can't do directly. You need to use a recycle, which is under logical ops. Energy, a recycle block, a mass flow recycle block. So that's just R. I'm going to put it over here more in the vein of the like the diagram that we've got over here in the Tut. So also, what I'm going to do now is to take this thing and flip it round. So I'm going to grab this, put it over here, and then if I right click on it, I can invert it horizontally. So that means it's going to go, instead of going from left to right, as is conventional in Western society, we always go from left to right, we're going to invert horizontally. Okay, and then this stream is going to go into, let's get the energy stream back at a reasonable place. And this is our outlet stream. That's the ammonia product. Yes, you can. So I'm not inverting this one yet because I'm going to attach it to this recycle. So I'm pushing the recycle up there, and then I'm right-clicking and inverting this one, because inverting it horizontally, so that this stream goes into so now we're going to connect this one into R. So the inlet stream is going to be MSTR08. Oh, look, I have to invert it. Sorry, Gareth. Invert horizontally. Okay. Now, for people with OCD, you can align them. In Aspen, there is an align blocks thing, which is really nice for OCD people like myself. Okay, so now we're going to connect recycle. We're going to create a stream on recycle. Outlet stream, and we can connect it to the mixer. We're going to create it, and we're going to connect it to the mixer. Oh wait, we'll do that in a moment. This must be MSTR11. Cool. I'm going to invert that one. Put it down there. Right. Recycle done. Whew. That's only one of them, and we still got to do another one. But let's see if it will actually run if we do this. So we try and solve the flow sheet. Last run execution time, everything is blue, so that runs. Yay! Applause! Next one. So the other one that recycles, if we look at our Tut, is this MSTR06. We've got to recycle now. All right. So now, as soon as you thank you. I'll take a bow. As soon as you do a gas recycle, and remember there is argon there. If you just recycle this gas, all of the argon is going to be put back in, and we keep on getting new argon in, and then this thing will never converge. And this is really the big thing about putting in recycles. Yeah, when you put in a recycle, this one is okay because we are taking out most of the stuff over here. So this recycle, we didn't need to put in a purge. This one, we do need to put in a purge. And for that, we need to put in a splitter. And that we will get mixer splitters. And we put in the splitter up here. And I am going to invert it horizontally, so that this stream can go into that stream. And that stream must be MSTR06. And we're going to create an outlet stream. Well, we're going to create two outlet streams. One of them is going to go away. And one of them, oops, and one of them, create, is going to be recycled this way. So I'm going to invert it. I'm going to put in another logical operator, recycle block up there. I'm going to invert it. I'm going to add oh, it wasn't selected. I'm going to add the inlet stream to be MSTR. I'll move it a little bit closer there. Otherwise, I run out of space. MSTR13 goes into the recycle block. And now we have to put in a mixer because we've got to mix before we go to the RC. Yes, we're going to the reactor directly. Right, let me just speak about the pressures here. We've made the assumption that there's zero pressure drop across here, and that there will always be some pressure drop, but it is possible to make the simulation run without putting in a compressor. You would need a compressor just to compensate for pressure drop if you put this recycle back in here. Both Aspen and DWSim don't require that. So this needs a mixer. I'm going to disconnect the MSDR02. Disconnect it. Put in a mixer. Create an outlet stream for the mixer. Right, I have to select it first. An outlet stream for the mixer. Create. Make that the inlet stream of this one. Inlet stream is MSDR 14. Right. Now, I'm going to add this one first because I think it adds them from the top to the bottom. Remember, I did this stream first and then I did this stream second. So when it puts them in top to bottom. So I prefer this recycle to be at the top, and that's why I'm going to add the. Oh, wait a minute. I'm going to create an inlet stream. And that one is going to be the recycle. And the outlet of the recycle, I'll invert that one. And then I'm going to add the stream, MSDR02 is the second stream in the mixer. Yeah, so there I've got it right. Just to make it look nice for people like me. Okay, and then we can go the recycle. We're going to be adding an outlet stream, which is MSDR50. Takes a bit of time, but there it is. And doesn't that look beautiful? Now let's see if we can get something to solve. And did we do everything? I don't think there's anything we have to put into mixers. Oh, the splitter we've got to choose. We've got to put in this split ratio. So this one must be 10%. MSDR must be 10%. So that is MSDR 12 is outlet stream 1. Must be 10%. So that all the way down, 12, 11, and 10. Then it's automatically solving. So now it's solving the two recycle loops simultaneously. Hoping we get this right. Seems to have stopped. Not calculated. Yeah. Well, this is the sort of thing I was getting yesterday, and I'm sure that many of you got the same sort of thing. Okay, so that's the one that we had to still specify, and we have now. What else did we add? We've added the connections. That's straightforward. This is still the same as it used to be. It goes straight into there. MSDR3, cool. this is all as we used to have it. And this recycled, it did work. So I'm just going to have a look at the numbers. All right, there we go. Maximum number of iterations. 392. Script data. Pascals, 20,000 pascals. Yeah. More fractions. 0.8, that's good. So let me have a look. We should have pretty much go to stream compound amounts, null fractions. We change to oh, nice. No, I've done something wrong. I just want to check that these are, there we go, 0.99 is the ammonia that's coming out here. And so that looks correct. So maybe I'm going to force another calculation, force solve. Still unhappy. All right, what I'm going to do is disconnect MSDR15 and force solve. Okay. I didn't do anything other than put in the recycle. Yeah, I'm very careful about putting in the recycle. I did make sure that everything was working before I put in this recycle. Obviously got something wrong. So I'm going to look at the unit operations and check that I've got the right conditions. Polytropic, outlet pressure 200 bar and 75%. Mixer, I don't think there's anything we have to change on it. The gas liquid separate. No, the reactor. This is the reactor. Let's just check that. Default set. I wanted to define outlet temperature, and that would be 250 degrees C. That was something I got wrong. Pressure drop is fine. Good. Oh, blah, blah. Right. Blue. Oh, okay. Oh, what a lovely color that is. Okay. Inlet stream is now MSDR 15. And I suspect it would have solved. No, it says solve flowsheet by pressing F5. Please. Yes. Okay. What I want to look at is the mass flows over here. Move this up that I can see the mass flow easily. Flow 18.7 kilograms per hour, and the Aspen gave 90. Yeah, so that looks right. Let's have a look at the mass flow rate of this stream, of this recycle, and that is 13 kilograms per hour. Over here we've got 8. So that's fairly different. But that's what we've been getting. Angelo, what was that star button? Oh, you made it thing. Where's the fancy align function? The fancy align function is align button is only in Aspen. I haven't found it here, but I want to show you something that you must not do. I did it yesterday. Right click. There's an option of auto layout. Don't do that. Don't do auto layout. Oh, that caused me a delay of about an hour. Add MSTR 3 and 4 to a mixer. Oh yeah. The reason it's an unnecessary complication. So if we have a look at this, you can see it's not. It's 10 to the minus 14 kilograms per hour. And that's just calculation error. Because we're operating at 250 degrees C, we are not going to get 250 degrees C. We're not going to get liquids, even at 200 bar pressure. So, I'm assuming we're never going to get liquids there, and that's why I just leave it as it is. But yes, sure, you could add a mixer. I'm just wondering, this is a reactor. If you right click on an open space, the second option, perform ATL, which you should not press. What a terrible button. Doom, despair. Okay, let's have a look at this one. MSTR 13. We've got 121 kilograms per hour. And on the Aspen, 127. So that's close enough for me. So I think it's solving correctly. And what I wanted to point out in this particular TUT is if you have a look at the outlet of this polytropic compressor, you'll see that the temperature is 1,321 degrees C. In the Aspen simulation, 1,226, again, close enough for me. This is why we don't. Now, what happens when the temperature rises is that we are compressing a greater and greater volume of gas. And the energy required to compress gas is integral of VdP, V dot, volume flow rate dP. And the volumetric flow, oops, keep on wanting to go and point at volumetric flow, 2.9 cubic meters per hour is probably at the outlet there. And let's have a look how much it is at the inlet. Oh, wait. Simply by pushing up the pressure, the temperature, you are increasing the volumetric flow. So I'm not going to look at the front because it will be less, because we've got a higher pressure here. So you don't want to have this isentropic temperature rise or polytropic temperature rise. Okay, the difference between the Aspen practical and this DWSim Tut is the Aspen compressor had the option of an isentropic compression, and this one is a polytropic, so this can include a heat rise, a enthalpic increase. So they will give different answers. But yes, what we do as soon as we have a very high ratio of pressure increase from there 1 bar to 200 bar, we're going to learn this in our heuristics that we only use approximately 3 to 4 times. So we'll first go from 1 to 3 bar. That'll push up the temperature, and then we cool it down again. And then we go from 3 bar to 9 bar, and then we cool it down again. From 9 to 27 bar, and so forth, until we eventually get to our 200. So that's something I wanted to point out on this flow sheet. And look at the time. Isn't that great? So anybody still struggling? Anybody got questions on this? Good stuff. Okay, then I'm going to stop the recording. For some reason, my temperature at MSGRO2 is wrong. I'll have a look at that. I'm going to stop the recording.